All right, we're going to walk through 6 fundamental concepts that are really the backbone of any data science project. We'll follow the logical workflow from the moment you get that raw data to the point where you're delivering some powerful insights.
Okay, so here's our game plan. We're starting with data exploration, getting our hands dirty. Then we'll figure out how to describe its shape, test our big ideas, compare different groups, make sure our models are solid, and finally, bring it all home by visualizing our findings.
First up, and I can't stress this enough, is the most critical phase of any analysis. You've got to get to know your data set inside and out.
This process has a name, Exploratory Data Analysis, or just EDA. Honestly, the best way to think about it is like a detective showing up to a crime scene. Before you start accusing suspects or building some grand theory, you just look around. You gather clues. You see what the data is telling you on its own terms.
So what are we actually looking for during EDA? Well, this is your chance to spot major problems. Things like missing values that could totally wreck your models, or wild outliers that might just be typos. You're also getting a feel for the data's structure, seeing how variables might be related, and just catching any weird inconsistencies. Basically, we're making sure the foundation is solid before we even think about building the house. So, once we have a feel for our data, how do we describe its shape in a more, let's say, mathematical way? We're going to look at 2 key stats that help us pin down its distribution and symmetry. First up is skewness. All this measures is the asymmetry of your data. If you've got a positive skew, that long tail stretches out to the right, and it literally pulls the mean to be higher than the median. On the flip side, a negative skew has a long tail to the left, which drags the mean down below the median. Why do we care? Well, a lot of statistical models work best when the data is symmetrical, so knowing the skew is a big deal.
Next is kurtosis. Now, this isn't about which way the data leans, it's about how peaked it is. High kurtosis means you have a really sharp peak and what we call heavy tails. That's just a fancy way of saying you're more likely to have extreme outliers. A great example is stock market returns. Usually they're calm, but those rare, huge crashes or spikes give the data high kurtosis. Low kurtosis, on the other hand, means a flatter peak and fewer outliers.
So here's the bottom line. Skewness and kurtosis give you 2 totally different pieces of the puzzle. Skewness tells you about the direction of the lean, which points to imbalance. Kurtosis tells you about the shape of that peak and how extreme your outliers might be.
All right, we've got a handle on our data's shape. Now, let's get into the formal process we use to make confident, data-driven decisions.
At the very heart of this are 2 competing claims. First, you have the null hypothesis. This is the boring, default assumption that there's no effect, no change, nothing interesting going on. Then you have the alternative hypothesis. This is the exciting part. It's the claim you actually want to prove. So imagine a company says its cereal boxes weigh 500 grams. The null hypothesis is that, yep, the average weight is 500 grams. Our alternative hypothesis, what we might suspect, is that the average weight is not 500 grams.
To settle this, we follow a superstructured 5-step recipe. First, we state our 2 hypotheses. Then we set our significance level, our threshold for proof. We choose the right statistical tool for the job. After that, we calculate something called a p-value. And all that is the probability of seeing our results if the boring null hypothesis were actually true. Finally, we compare that p-value to our threshold and make our decision.
And that threshold, that significance level, it's almost always 0.05, or 5%. Think of it as the bar we have to clear. If our calculated p-value is less than 0.05, it means our result is so rare it's highly unlikely to be just random chance. That gives us the green light to reject the null hypothesis. There's a common saying that's really helpful. If the p is low, then no must go.
Okay, let's move on to a super common task, comparing the average values between different groups. We've got 2 main tools for this, and knowing which one to grab is absolutely essential.
So, t-test or ANOVA? The choice boils down to one incredibly simple question. How many groups are you comparing? If the answer is exactly 2, you use a t-test. The second you have 3 or more groups, you have to switch over to ANOVA, which stands for Analysis of Variance. It's that simple.
And ANOVA is a really flexible tool. A one-way ANOVA is when you're looking at just one factor, like comparing test scores across 3 different classes. A two-way ANOVA lets you look at 2 factors at once, like the effective teaching style and the gender of the student on test scores.
And then there's repeated measures ANOVA, which is perfect for when you test the same people multiple times, like checking their health before and after a new treatment.
So you've done all your analysis, you've built a predictive model. That's awesome. But how do you know it's actually any good? How do you know it'll work on brand new data it's never seen before? Let's check out 3 techniques to make sure our model is reliable.
The go-to method here is cross-validation. Its whole purpose is to prevent a huge problem called overfitting. That's when your model basically memorizes the training data, so it looks great, but then completely falls apart when it sees new data. With cross-validation, you split your data up, maybe into 10 parts. You train the model on 9 of them and test it on the one you held out. Then you just repeat that process for each part, which gives you a much more honest assessment of how it'll perform in the real world.
Now, an extreme version of this is called Leave One Out Cross-Validation, or LOOCV. And it's exactly what it sounds like. You train the model on your entire data set except for one single point, and then test it on that one point. And you do this over and over again for every single data point you have. It's incredibly thorough, but as you can probably guess, it can take forever to run on a large data set.
And finally, we have bootstrapping. This is a really cool resampling method. What you do is create a bunch of new, fake data sets by just drawing samples from your original one. The trick is you do it with replacement, meaning you could pick the same data point more than once. This is an awesome way to understand the stability of your model and estimate its uncertainty, and it's a lifesaver when you're working with smaller data sets.
Okay, after all that hard work, the cleaning, the testing, the modeling, we get to the final, and I'd argue the most important step, communicating what you found. A brilliant insight is totally useless if no one can understand it. This is where you become a storyteller.
You've got a whole toolkit of charts and graphs, and the secret is just picking the right one for the job. Trying to compare totals between categories? A bar chart is your friend. Want to show how something changed over time? Go for a line chart. Need to see the distribution of a single variable? A histogram is perfect. Each one is designed to answer a different kind of question in a way that's instantly understandable.
And let's be super clear, this is not about making pretty pictures. Good visualization turns a dense spreadsheet of numbers into something a human can grasp in seconds. It allows leaders to make quick, informed decisions. It can even help you spot anomalies you might have missed. But most of all, it's how you tell a compelling, memorable story with your data, a story that actually leads to action.
So we've walked through the whole workflow, from that first look at the data all the way to the final presentation. These aren't just a bunch of abstract rules. They're the tools you use to make discoveries. So the real question to ask yourself is, now that you have the framework, what story is your data just waiting to tell?